Hello friends, I welcome you in lecture number 22 on complex integration. In this lecture also we will discuss two more examples on extension of Cauchy integral formula. In lecture number 21 we have seen that if we have a function f of z which is analytic everywhere inside and on some simple closed contour denoted by capital C, and if z0 is any point which is interior to this simple closed contour, then integral of f of z divided by z minus z0 to the power n plus 1 with respect to z along this contour is given by 2 pi I divided by n factorial, and if we have n plus 1th power of z minus z0 here, we will take nth derivative of this function f of z at point z0, and this is true for n equal to 0, 1, 2 and so on. So today also we are going to discuss two more problems on the extension of Cauchy integral formula. So we will remember this result. For n equal to 0 we will have 0 derivative, that is function itself at point z0 multiplied with 2 pi I, because 0 factorial is 1, and in that case we will have this Cauchy integral formula for n equal to 0. Therefore this is an extension of this Cauchy integral formula. So this example we consider evaluate integral of function 1 over z cube z plus 4 with respect to z, where C is the circle with center 0 and radius 2 described in the positive sense. So first we observe that given function is 1 divided by z cube times z plus 4, and this is rational function and it is analytic at every point except those points where denominator is 0. So here denominator is 0 if z equal to 0 and z equal to minus 4, and our contour is circle with center 0 and radius 2. So it is clear that z equal to 0 is inside this circle. If I take absolute value of 0, I will obtain 0 and it is less than 2. Therefore z equal to 0 is interior to this circle, and for z equal to minus 4, if I take absolute value of minus 4, I will have 4 and that is greater than 2. Therefore z equal to minus 4 is outside this circle. So to use extension of Cauchy integral formula, we will write this function as, we will write z cube in the denominator, and here we will write 1 divided by z plus 4, and this 1 divided by z plus 4 we will consider as f of z, and this z cube can be written as cube of z minus 0, and this 0 is interior to given simple closed contour which is a circle with center 0 and radius 2. So now our integral can be written in this form. Integral of this along given contour is equal to integral in this form. So we can use Cauchy integral formula. This 3 can be written as 2 plus 1. So this is going to be equal to 2 pi I divided by n factorial, that is 2 factorial, and second derivative of f at point z0 which is 0. So we have to understand this first, that how we can express our integrand such that we can apply Cauchy integral formula. So to apply Cauchy integral formula, our integrand must be in this form, f of z divided by z minus z0 to the power n plus 1. So here we find that if we take f of z equal to 1 divided by z plus 4, then it is analytic everywhere inside and on this simple closed contour, and we have z0 equal to 0 and n plus 1 equal to 3, that is n equal to 2. So we have to consider second order derivative of this function 1 over z plus 4, and we have to write all these things systematically we first write down f of z is equal to 1 divided by z plus 4, and we first calculate first two derivatives of this function. We will require them. So f dash z is derivative of 1 by z is minus 1 by z square. Here instead of z we have z plus 4, so this is going to be minus 1 divided by z plus 4 square into derivative of z plus 4 here. So derivative of z plus 4 is 1 plus 0, that is 1. So that is by chain rule, and this is minus 1 divided by z plus 4 square. So we can write our function f dash z as minus 1 times, we can rewrite 1 over z plus 4 square as z plus 4 to the power minus 2. We again differentiate with respect to z. We know that if we have z raised to n, then derivative is n times z raised to n minus 1. So here we apply that formula. Instead of z we have z plus 4. This minus 1 as it is, power is minus 2. So minus 2 times z plus 4 to the power minus 2 minus 1, that is minus 3. And because I have z plus 4 instead of z, I have to apply chain rule, and in the bracket I will write derivative of z plus 4, that is 1. So finally this becomes f double dash z second derivative equal to minus 1 into minus 2, 2, and this I can rewrite as z plus 4 to the power 3, and I will require this derivative at z equal to 0. So let me calculate at z equal to 0 from this. This is 0 plus 4 cube, so this is going to be 2 divided by 4 cube, or this we can rewrite as 2 divided by 4 into 4 square, and these 2 will get cancelled, and 4 square is 16 times 2, that is 1 divided by 32. So this we can rewrite in another notation as second derivative of f of z at 0 is 1 divided by 32. Then we have to write down information about given contour. Given contour is circle with center 0 and radius 2, and we know that circle is simple and closed, so we require simple closed contour, which is simple closed contour, and our f of z is 1 divided by z plus 4. This is analytic everywhere inside and on this simple closed contour is analytic everywhere inside and on this simple closed contour C. Because this function is not analytic at z equal to minus 4 only, and z equal to minus 4 is outside this circle. Therefore, this function is analytic everywhere inside and on this simple closed contour, and z equal to 0 lies inside this circle or inside this simple closed contour. So we require these conditions to apply Cauchy integral formula. So we have to first write all these things, and therefore by Cauchy integral formula we have integral of f of z divided by z cube with respect to z along the circle mod z equal to 2. This I can rewrite as f of z divided by cube of z minus 0, and this I can rewrite as 2 plus 1 integral along contour C. and this by Cauchy integral formula. Here n equal to 2. So we have 2 pi I divided by n factorial, n is 2, and here I have n equal to 2, so I have to write second derivative of f of z at point 0, and we have obtained this, and 2 factorial is 2, so that will get cancelled with this, and this we have obtained as 1 divided by 32. So we have pi times I divided by 32, and f of z is 1 divided by z plus 4, so that we can substitute here. Therefore we have 1 divided by z cube times z plus 4 integral is pi times I divided by 32 along given circle mod z equal to 2. And we can see this is very easy. All we have to decide is how we can write our integral in this form, and we have to check whether these conditions are satisfied to apply Cauchy integral formula or not. I have taken another problem also. Evaluate integral of z minus 1 divided by z plus 1 square times z minus 2 with respect to z, where this C is the circle whose center is I and radius is 2. And we can observe that this is rational function, division of polynomials. Therefore it is analytic everywhere except those points where denominator is 0, and denominator becomes 0 for z equal to minus 1 and z equal to 2. So first we have to check that out of these 2 points which point is inside this circle. So to check that, we can put z equal to minus 1 in this left hand side. First we check for z equal to minus 1. So I am putting z equal to minus 1 here, that is absolute value of minus 1 minus I, and absolute value is given by square root of square of real part which is minus 1 plus square of imaginary part which is also minus 1. So this is going to be square root of 1 plus 1, that is square root of 2, and square root of 2 is less than 2. So what we can say is z equal to minus 1. Here I have taken z equal to minus 1, and I find that absolute value is less than 2. So I can say that z equal to minus 1 lies inside this circle mod z minus I equal to 2. And if I take z equal to 2 in absolute value of z minus I take z equal to 2. So now real part is 2, so square of 2, imaginary part is minus 1, and this is going to be 4 plus 1, that is square root of 5, and that is going to be greater than 2, because we know that 5 is greater than 4. So if we take square root on both sides, we will have square root of 5 is greater than 2. That means this z equal to 2 lies outside this circle. For z equal to minus 1 it is inside this circle, for z equal to 2 it is outside this circle. Therefore z equal to 2 lies outside circle, absolute value of z minus I equal to 2. So once we decide that which points are inside the circle and which points are outside the circle, we will be able to write our integral in this form: f of z divided by z minus z0 to the power n plus 1. So now our circle is absolute value of z minus I equal to 2, and we have seen that z equal to minus 1 is inside this circle and z equal to 2 is outside this circle. So if I consider f of z equal to z minus 1 divided by z minus 2, then that function is analytic everywhere inside and on given circle, because this function fails to be analytic at z equal to 2 only, but z equal to 2 is outside this circle. So if I take f of z equal to z minus 1 over z minus 2, then this function is analytic everywhere inside and on this circle. And here if we compare with this, then z0 is minus 1 and minus 1 is inside this circle. So now if I take f of z equal to this, then our integral can be written in this form, and f of z becomes analytic everywhere and inside this circle, and z equal to minus 1 lies interior to this circle. Therefore we can apply Cauchy integral formula. And if we compare this n plus 1 and 2, we will have n equal to 1. That means we have to find out first derivative of this function at z0 equal to minus 1. And we have to write all these things systematically. So first we write down that f of z, we denote this function z minus 1 by z minus 2 by f of z. Let f of z equal to z minus 1 divided by z minus 2, and we know that because this is division of two polynomials, this is analytic everywhere except z equal to 2, and z equal to 2 is outside given circle that we have seen, which lies outside given circle denoted by C. This means our function is analytic everywhere inside and on this simple closed contour C. Therefore f of z is analytic everywhere inside and on given circle, which is absolute value of z minus I equal to 2 and z equal to minus 1 lies inside this circle C, and therefore we can apply Cauchy integral formula by Cauchy integral formula. Integral of f of z divided by square of z plus 1 along contour C, that is equal to this. I can rewrite again as f of z divided by z minus 1. 2 can be written as 1 plus 1 dz along this circle, and this is by Cauchy integral formula 2 pi I divided by n is 1 here, and first derivative of this function f of z at z equal to minus 1, and 1 factorial is 1. Therefore 2 pi I times f dash at minus 1. Now we have f of z equal to z minus 1 by z minus 2. So now we calculate first derivative and then we will substitute it. So f of z is z minus 1 divided by z minus 2. To apply to find out derivative, we have to apply division rule, which we are applying in real analysis. We will write square of z minus 2 in the denominator. Here we keep z minus 2 as it is, and we take derivative of z minus 1, which is 1. Then minus z minus 1 as it is, derivative of z minus 2, which is 1. And this I can simplify as z minus 2 minus z plus 1 divided by square of z minus 2, and z will get cancelled and we have minus 2 plus 1, that is minus 1 divided by z minus 2 square, and we require value of this derivative at z equal to minus 1. So here we put z equal to minus 1, and we will have minus 1 minus 2 square, that is square of minus 3, which is 9. So first derivative at minus 1 of f of z is minus 1 by 9, that we can substitute here. So finally our integral is therefore integral of f of z divided by z plus 1 square along contour C equal to 2 pi I into f dash at minus 1, which is minus 1 by 9, and f of z is z minus 1 divided by z minus 2, so that we can substitute now. So we will have given integral along given circle is minus 2 pi I divided by 9 by extension of Cauchy integral formula. So these are very nice problems. All you have to understand is which function you have to consider as f of z from the given integral, and you have to also check that whatever function you take as f of z, that must be analytic everywhere inside and on given simple closed contour, and whatever power is here, suppose here power is n plus 1, then we are considering nth derivative of f of z. If power is 4, we will go up to third derivative. If power is 3, we will go up to second derivative. Here power is 2, therefore we have obtained first derivative of f of z at z equal to minus 1. So this is all about this session. I hope you like it. Thanks for watching.